So let's start with this second part dedicated to global information about the Mercury surface. And as you can see from the program, we have separate in some way the part related to a general information of the surface composition with respect to just the more specific information from the reflectance spectroscopy. This is mainly due because thanks to the messenger mission, we have a wide range of information of the Mercury surface composition. And so was, I think, helpful to enter in a global view in detailed information than to speak about what really is from our side important to addressing composition information into a map. So sorry, I have just to move to the next. Okay, but just looking before messenger, what was possible to know until 2008, we can say from the messenger, from the Mercury surface, was just few type of multispectral information from Earth-based instrument that permit to see a sort of red slope spectra in the veneer that was compared and similar to the one of the lunar anorthosite. For this, before messenger, we were considering strongly Mercury similar to the moon, even from a composition point of view. And in particular, we were considering Mercury as a primary crust surface. We have already seen from Valentina's talk that this is not what we know now, but just to let you know that until more or less 12 years, 13 years ago, this was the situation for the composition. No more data we had. And we were really considering that the Mercury surface was a primary crust surface. Then we have messenger, and we have started seeing that the surface was not black and white, or we can say was not mainly divided, as we can see for the moon, with specific composition dedicated to the Maria and specific composition globally, considering in a globally way the composition of the island. But we have a clear variegation. Those are products related to the veneer camera, and Francesco will talk more about that after my talk. But it was just to give you already an idea that the surface of Mercury is strongly variegated, and there is no, we can say, a sort of big domain of Maria, basaltic Maria, with respect to an island crust. And this was confirmed by the camera studies and so from the morphology, but it's clearly evident also from the compositional point of view. This heterogeneity is also partially studied by a larger number of information that we have from messenger mission that was related to the elementary composition. I will say largely because the resolution of those instruments were lower with respect to the cameras and the spectrometers, but still we started to see that there is some regions that are strongly compositionally different from other. Just remembering what permit us to have information from the messenger mission are mainly two different instruments. So X-ray spectrometer that permit to have information, in particular at global view or almost a global view for 5 different elements. So magnesium, aluminum, calcium, sulfur, and iron. And this kind of instrument permits to have information at millimeter scale depth. Then we have the information from a gamma ray spectrometer that for some element like potassium, sodium, and partially other like aluminum, calcium permit to have information at and also carbon in we can say globally distribution or partially coverage of the surface of Mercury, but with an opportunity to map this information. For other elements, as well for other elements for the X-ray, we have just a sort of threshold limit thanks to the global average information. And just to enter a little bit more in detail, what we can have is this is a clear map of an element thanks to the X-ray, and you can clearly see the global distribution of this element that is magnesium on the surface of Mercury. Another point that have to be remarked is that since the condition of Mercury orbit, the messenger orbit, the northern are better resolved than the southern region. So at north, we have an higher resolution, and this is one of the regions probably why for all of these elements, we see less contrast on the south with respect to the north regions. Anyway, already from magnesium map, for instance, we can clearly see that some regions are strongly enriched as some areas are strongly depleted of this element. The gamma ray have a lower resolution and mainly give a result in the north region of Mercury. But even here, for some elements, it was possible not to have just a global value for an average for all the surface, but having a mapping of the surface of some elements. And I was saying these are mainly sodium and potassium that can clearly map on the north, but even some other like aluminum, calcium, that even if a lower scale was more or less confirming what the X-ray information was telling us. Another important aspect that has to be in mind to the information from the gamma rays is the information related to the thorium and to carbon that, as we'll see, give important new knowledge about Mercury's composition and potential Mercury evolution. If we enter a little bit more in detail on this information, we can see the distribution for some of this element to the overall of the surface. And we can clearly that, for instance, starting from those that permitted from the beginning more or less to have a global coverage, there is variation that strongly, in some cases, are, we can say, complementary. So if we look magnesium silica map, we can clearly see that there is a region that is mainly enriched by magnesium, whereas we have some regions that are mainly depleted in magnesium, like the northern plains and the Caloris Basin. If we look the aluminum silica map, we can clearly see that the regions correlated to the magnesium silica enriched area are mainly depleted in magnesium. But at the same time, we can clearly see that if Caloris Basin that was depleted in magnesium is enriched in aluminum, this is not true for the northern plains, where both magnesium and aluminum seems to be relatively poor. We can even see then for some other regions, like the regions that are east to Rachmaninoff, we have a relatively lower values of magnesium, whereas we have some enrichment in aluminum. And so there is clear evidence of heterogeneity in composition of the Mercury surface. Other three elements I would say was mainly mapped on the Mercury surface, and they are sulfur, calcium, and iron. And they are also telling something very important. First of all, we already heard from the Valentina's presentation that Mercury is not so depleted in volatiles like we were thinking before messenger mission. And this is confirmed by the sulfur values that are mainly relatively high at the Mercury global view, but there is some regions in particular that are strongly enriched, like some portion of the high magnesium region that we have seen before. And often we can clearly see a correlation of regions that are enriched in sulfur and enriched in calcium. Another important aspect that we had as confirmation was already in some way supposed before messenger, but was confirmed by different type of data from the messenger mission, is that iron on the surface material is very low. So we can see that there is a very low values of iron versus silica, and then we'll see later on that this was in some way translating in values that are lower to probably 1% of iron, or at maximum 2% in the regions where iron is relatively enriched. This kind of information from X-ray permitted to start to try to make some hypotheses of the type of material and on the differences of the regions. And you can clearly see as first that previous relationship between magnesium and aluminum moved to suppose that the composition of mercury was closer to basaltic towards komatitic composition. And so not so far from some of the material that we can see also on the Earth. But what we have to remember and to take into our mind is that they are almost iron-free, something that is completely different for volcanic materials from all the other differentiated bodies, considering Earth, Mars, Moon, or Vesta, for instance. For all of them, we have strong enrichment of iron in lava's material. But then what we can clearly see also is that there is an opportunity, a first opportunity to differentiate those information in different regions from a compositional point of view. Mainly this week is possible to be done on the north due to the resolution of this instrument, and mainly can be done, we can say, at this point to some large areas. But clearly it was possible to separate, as already called before, an high magnesium region, where substantially we have higher values of magnesium on the planet, and correspond often with higher values of sulfur and calcium. Then we have the northern plains that was clearly distinct by the rest from a morphological point of view, but even from some compositional information, it's possible to separate from the surrounding terrains. And even considering the variegation of the information from X-ray and gamma ray, was possible to separate the northern region of the lava, the volcanic plains from the north, with respect to, we can say, the southern portion of this lava. And this mainly division can be done considering the different abundance of magnesium, but even the different abundance of sodium, because as we have seen before, sorry, I'm going slightly back, potassium and sodium are enriched in the northern area with respect to the southern area. And so this volcanic plains can be clearly divided in a region that has intermediate in magnesium, those green, and has slightly poor in sodium and potassium with respect to those that are lower in magnesium and have higher values of sodium and potassium. Then we have already seen that caloric basins look like different to the rest, with in particular relatively low magnesium and high aluminum variation, and even some small region like Rachmaninoff can be differentiated for some elementary variation. This was, we can say, strongly evidence that there is heterogeneity on the surface that still is debated is due to heterogeneity on the metals or influence of impactors or something like that, but permits to have a clear evidence of some variation in the composition of the material on the surface. Recently, Nitter et al. Update the maps with some new correction and new data analysis, so for some elements at wider distribution, but they more or less confirm the result that was already published in 2015. But much more we can see as some regions appear differentiated when we compare. So here is the map of magnesium and silica and aluminum silica. The variation of the two elements are more or less those that were already published in 2015. There is some specific regions that are enriched in magnesium, for instance, and depleted in aluminum, or some regions that are enriched in aluminum and depleted in magnesium. But strongly, when we start to compare those, we can clearly see that some of these regions are possible to be separated, and still we have the high magnesium region that can be separated thanks to the high values of magnesium and low values of aluminum, as well as the caloric basin can be separated thanks to the higher values of aluminum and the lower values of magnesium. But you can clearly see that even some other regions that are less studied can be clearly separated, and even within the northern volcanic plains, probably the heterogeneity could be higher than what we know just today. Here you can clearly see the final map of sulfur and calcium. And again, you can see that the magnesium region seems to be enriched on sulfur with respect to the rest of the planet. And the same area is generally enriched or slightly enriched in calcium abundance. What is also interesting, if we just compare the ratio between sulfur and calcium, we can clearly see that anyway, the variegation on the surface is relatively low, with just low values of calcium-sulfur ratio, with the exception of some regions, in particular closer to Natair Facula. And this is something also peculiar, because Natalia Facula is a region that is volcanic with pyroclastic deposits, and so maybe thought that volatile material could be present, and so the hypothesis that sulfur could be abundant in this region is instead misled by this ratio, because calcium seems to be strongly enriched in this region. But if we look at the map of calcium and sulfur, in reality, what we clearly see is that there is slightly enriched, but not so much on calcium, but there is a region that with a strongly depletion on sulfur. And so even this is something that is peculiar information that still is to be deeply investigated, but gives some, we could say, fascinating reason to study better Mercury with the following mission. And this is the final map of iron. And still we can clearly see that in particular, there is an enrichment of iron in some portion of the high magnesium region. Some other regions seems like to have an enrichment of iron, but if we compare with the standard deviation, so the error of these maps, so we can clearly see that just the area within the magnesium region have higher values of iron with not an higher values of error. So those regions are still under debate if they are really enriched on iron, or there is much more effect of the error on the information. So something that has to be better considered from the analysis of this data. Once and finally, the other important information that we have retrieved was I say that there is volatile element, and even the abundance of sodium and potassium seen in the north are higher with respect to what was expected on the Mercury surface, and still push in the fact that Mercury is slightly enriched on, we can say, volatile or elements, or elements that can be mobilized. This is something that has to be still understood if it's related to the different composition of the primary lavas that was emitted, or there could be some enrichment due to other process on the surface of Mercury. But still, as already anticipated before, there is a clear evidence that the northern terrains are enriched in sodium and potassium, and there is a sort of this distinction, even if at relatively low scale resolution of the data that we have on the distribution of this element within the northern volcanic terrains. Another important thing was that since we have the opportunity to have potassium and thorium from gamma ray, the relationship between potassium and thorium is strongly different from what was achieved for the lunar surface. And this again push in the direction that the Mercury surface, that for some point of view can be similar to the moon surface, is instead different from an evolution point of view. And so the surface of Mercury has had a completely different evolution with respect to the Moon one. And moreover, it's particularly interested that this potassium thorium lines that we can have from the messenger's data are closer to the lines that put also the information from the Mars surface and the oceanic crust of the Earth. So it looks like that the relationship between volatiles and refractory elements on Mercury is closer to Mars and Earth with respect to the Moon. The other important aspect that was achieved in 2015, so already at the end of Messenger mission, was the fact that the neutron spectrometer investigated in some region absorption that was at the end possible to compare with absorption related to carbon phases. And 3 different locations was evidencing different values of neutron absorption that was possible to compare with different potential abundance of carbon phases. As you can see from this plot that relate the carbon abundance with the neutron residual. And this is something that is quite important because we know that there is some low reflectance regions, and those 3 regions that was enriched on this carbon was correlated with some of this low reflectance material. And seems like that there is also a relationship on some parameters that we can obtain from the MDIS dataset, so the different channels of the cameras that permit to relate the variation of these 3 sites that are these 3 blue square on the right plot and compare with the carbon abundance. So it seems like that these parameters, we can say band depth, but in truth is a change of slopes around 600 nanometer, permit to have a correlation from the reflectance properties to the abundance of carbon. And some authors try to extrapolate this for other low reflectance region, evidencing how at maximum we should have 5% of carbon in some of this low reflectance material. And this is something important and to be taken into account for the study of the evolution of the crust, because this region could be probably the remaining of some, we can say, of the primary crust of Mercury. So those crusts that eventually at the beginning of the mantle ocean could quickly cool and give the formation of a floating crust that probably could be related to the presence of carbon, and so related to material that are carbon dominated. Then it's clear that once we have this kind of data set, the first idea is try to model the composition, try to understand which could be the composition of the rocks that are present on the surface. We have to remember that the information that we have directly is a ratio between the information of some elements with respect to the silica. So we don't have the silica values from the surface of Mercury, and so we cannot have directly oxide values of the different elements. But with different type of approach can be tried to be model the abundance of the oxide. And one of these in general is to consider the distribution of the 5 major elements, so magnesium, aluminum, calcium, iron, and sulfur that we had from the X-ray, and close it to 100 and recalculated the and silica, obviously close them to 100 with just the silica as unknown, and so retrieve the oxide variation of the material present on the surface, so in the rocks that we have on the surface. And this was done from different authors. The first one was probably Charlier et al. That tried to model this composition, and they start to see that probably what we have on the surface of Mercury is much more correlated with the composition closer to terrestrial boninites with respect to comatites. This mainly due to the fact that probably the silica abundance, so the CO2 abundance on the rocks are slightly higher than what generally we consider for the limit of the comatites. And maybe some basaltic comatites could be closer. So we start to move from the first assumption that maybe we were looking to material that are closer to comatite to something that is slightly silica rich, so closer to boninite. We are speaking to comatites and boninites and not directly to basalt because the mafic material is almost magnesium. So having so low values of iron and considering the separation of the definition of the terrestrial rocks, we are moving to basaltic and boninites as a compositional type of rocks. This was partially confirmed even considering the relationship between aluminum and silica. Whereas we start to compare calcium and magnesium, we start to move in something that is between. So the boninites are not the best candidate because generally they have lower calcium with respect to what we have retrieved from, lower magnesium with respect to what we have confirmed, we have seen or calculated from X-ray information, whereas the range of calcium is more or less compatible for both boninite and comatite.
5 minutes.
Perfect. So starting from this and considering the possible composition, some authors start also to try to make some petrological experiment, and this permit to have try to have an evidence of starting from those potential composition, what we can differentiate with a crystal fractionation to see evolving a system from reducing the temperature, so from a melt point to crystallizing minerals, which are the differences between the different potential compositional regions, and so which different phases we are going to separate at which temperature. And so at the end, try to produce a sort of global modal abundance of the different phases. And we can clearly see the different distribution of those materials in the surface of Mercury, and we can clearly see that generally pyroxene and olivine can be the main phases with plagioclase, obviously, and it's clearly clearly evident that, for instance, the region that are higher in magnesium are probably a higher abundance of olivine with respect to pyroxene and plagioclase. So probably they have much closer composition to the Mercury mantle, but still is debated. The other point that clearly reached from this information is that considering the anomalous sulfur content, the surface, the compositional surface the compositional evolution of the material was has to be considered at stronger reduction condition with respect to all the other terrestrial bodies. Moreover, still from a petrological point of view, considering the potential mantle composition, thanks to the information of the composition of the surface, was clear from some experiments that just graphite, so carbon phases, could build a floating crust on the magma ocean. And the hypothesis was that considering this, the primary crust of Mercury could be made by graphite, and later on, the volcanism have just covered it, and just in few areas where we have the low reflectance material, this could be excavated. This is something that still is not, we can say, deeply investigated or give different evidence from the model that was done before to messenger mission or just closer to the messenger mission about the evolution of the crust and the mantle. So still, we are at the point that more information probably we need to better enter in the details related to the differentiation of the composition abundance in the inner crust of Mercury, and to understand better the relationship between the differences in composition from the mantle to the crust. The last proposed was still in 2009, so before to have a complete knowledge of the data of messenger that was related to a potential magma ocean that was considering a sort of overturn in the second moment. So the production of first differentiation with some material that was too dense closer to the surface, and then this was we can say collapsing, giving potential volcanism that after the first formation of the magma ocean. But this is something that still has to be better investigated now, thanks to this result, and probably will be improved thanks to the Bepi Colombo information.